So, last time we proved that an Artinian ring has only finitely many maximal ideals. Right. So, we showed that any prime ideal of an Artinian ring is maximal, okay, and it has only finitely many maximal ideals. So, which means if you look at the nil radical is some intersection of M1 up to Mn, right. Sorry, yeah, this is Jacobson's radical as well as nil radical, because in our Artinian ring there are all prime ideals are maximal. So, nil radical is equal to the Jacobson's radical in a Artinian ring. So, now see if you look at the Artinian ring, see if your nil radical is finitely generated, okay. If your nil radical is finitely generated, that means I can write this as x 1 up to x n some x r. Each one will have some, each x I will is nilpotent, therefore, x I power n I is 0 for some n I. If I take n to be summation over all those n i's, n power that n will be 0. The max, see x I power n I is 0 because they are all nilpotent, and if I take this to be summation n I from 1 to r, then this is 0. Right. Every element here is generated by some x 1 power alpha 1, x 2 power alpha 2 up to x r power alpha r, where summation alpha I is capital N, but summation alpha I is summation n I, means at least one of the n i's will be bigger than equal to alpha I, sorry, at least one alpha I will be bigger than equal to n I, that means that will be 0. So, therefore, this n power n is 0. So, nil radical is nilpotent if it is finitely generated, but is that true? I mean, can we, without even assuming, can we say that it is nil radical is nilpotent? Okay. So, let us try to see whether, you know, let n be A be an Artinian ring, M1 up to Mn be maximal ideals of okay. We know that there are only finitely many maximal ideals. Okay. So, I want I know, okay. So, let n be the nil radical of A, which is M1 intersection Mn, because all prime ideals are maximal. So, A nil radical of A is precisely this. Now, there is a, given any ideal we have, we can, you know, form a descending chain of ideals. Then for the chain n contained in n square contained in n cube and so on. See, this is, we are inside an Artinian ring. So, therefore, if we look at this chain, I can always find a k such that n k is equal to n k plus 1 and so on, right. This implies there exists a k in n such that n power k is equal to n power k plus 1, so on. See here, the question is whether this is 0 or not. Again, you know, this is nil radical is Jacobson's radical. If this were, you know, if your ideal n were finitely generated, again from here one can conclude that n power k is 0, because I can write this as n times n power k. So, n power k is n times n power k, n is an ideal contained in the Jacobson's radical. So, by Nakayama lemma this n k has to be 0, but again at the moment we are not in a position to apply Nakayama lemma, because we do not know whether the nil radical is indeed finitely generated or not. So, therefore, let us continue. Let us suppose this is non-zero. Okay. So, there is, so what we are saying is that n k is equal to n k plus 1. Now, n k is non-zero means n k plus 1 is non-zero and so on and so forth. So, consider the set called this S, set of all ideals of A such that j n power k is non-zero. Okay. I look at all ideals of A with the property that j n k is non-zero. Okay. This is a non-empty collection. I'll write it as proper ideal. This is a non-empty collection. Why is this a non-empty collection? N belongs to S, right? This n k, this is n times n k, and this is non-zero. Therefore, n belongs to this one, right? N is in S, S is non-empty. Now, we are in an Artinian ring. Every collection of ideals has a minimal element. In the Noetherian ring case, every collection of ideals has a maximal element. In the Artinian case, every collection has a minimal element. So, S has a minimal element. Say call that j naught. Okay. So, j naught is a minimal element such that j naught n power k is non-zero, therefore, there exists at least some non-zero element in j naught. So, let 0 not equal to some c in j naught be such that c n power k is non-zero. But then that means the ideal generated by c n k is non-zero, or in other words j naught is minimal, therefore, j naught has to be equal to the ideal generated by c. Since j naught is minimal in S, j naught equal to the ideal generated by c. let I be equal to n power k. Okay. Then what we know is that Ci Ci times I, this is Ci square, but Ci square is same as Ci itself. Okay. This is, see, I look at the ideal C n power k. If I multiply by n power k, what I get is C n power 2k, but C n power 2k is same, I power n power I power 2k, or sorry, n power 2k is same as n power k, therefore it is Ci itself. So that means Ci, so what we have shown is that C n power k, the ideal C n power k acting on and multiplied with C n power k is same as C n power k, which is non-zero. So we have reduced this ideal further. See, we have got a minimal element j. In j I have a non-zero element C, I have a minimal element j naught, I have a non-zero element C in j naught. Then what we showed is that j naught has to be equal to the ideal generated by C. Now further I reduce it further here, I look at the ideal generated by C n power k. What we are showing is that C n power k multiplied with n power k is again non-zero. C n power k is contained in C n power k is contained in C, therefore by the minimality C n power k has to be equal to j naught, or which is equal to C. Is contained in, so this implies that this is equal to ideal generated by C, which is equal to j naught, since j naught is a minimal element. So therefore C is equal to C times x for some x in n power k. C times 1 minus x is 0. But now what is x? X is in n power k. It's a it's in Jacobson's radical. No, it's a nilpotent element, right? X is nilpotent, n power k is again contained in nil radical, therefore any element here is nilpotent. X is, if x is nilpotent, what can you say about 1 minus x? It is a unit, right? Since x is nilpotent, 1 minus x is a unit in A, and that would imply that C times a unit is 0 will imply that C is 0. But C is 0 means that our j naught is 0, and that would imply that that was a contradiction to this assumption. Okay, which contradicts the assumption that C n power k is non-zero. So therefore n power k is 0, that is, so ultimately what we have shown is that in an Artinian ring the nil radical is nilpotent. Is the proof clear? So, in an Artinian ring, the nil radical is nilpotent. Now, if you recall, we had proved some time back a result that if you take a ring in which the 0 ideal can be written as product of maximal ideals, some finite product of maximal ideals, then the Artinianness of A and the Noetherianness of A are equivalent. Okay. Now, look at the situation where we are in. A is in an Artinian ring, the nil radical is nilpotent. So, if we start with an Artinian ring, every prime ideal is maximal. So, nil radical and there are only finitely many maximal ideals. So, nil radical is a finite intersection of maximal ideals. Okay. Now, look at the this says that so if you look at the intersection, the product is contained in the intersection, right, the product of ideals I times j is contained in I intersection j. Now, M1 up to Mn, the product will be contained in M1 intersection up to Mn. Now, look at the product, the n power k. N power k is 0, which means M1 power k, the product M1 power k up to Mn power k, that will be contained in n power k, but that is 0, therefore, this is 0. So, now 0 is product of maximal ideals. What does that mean? So, we are starting with an Artinian ring, which means the ring is Noetherian. So, what we have shown, what we have seen now is that a Noetherian ring, an Artinian ring is indeed a Noetherian ring. We have seen this is not true in the case of modules, right. We have seen Artinian module which is not Noetherian. We looked at this Q mod Z and subgroups of some subgroups of Q mod Z, which has every descending chain terminates, but you always have a ascending chain which never terminates. So, a Noetherian, an Artinian A module need not be Noetherian A module, but now in this case we are seeing that an Artinian ring is always a Noetherian ring. So, let us write this down. So, now you see, once we say that an Artinian ring is Noetherian, this makes perfect sense, because nil radical will be finitely generated. In the Noetherian ring, nil radical is nilpotent. Once it is finitely generated, this is, one can prove that way, or if Artinian ring is Noetherian ring, then nil radical is nilpotent again. So, an Artinian ring is Noetherian. So, let A be an Artinian ring. Let M1 up to Mn be the only prime equal to maximal ideals of A. Then n power, so let n be equal to M1 intersection Mn, then the product M1 up to Mn is contained in N. This implies that 0 is equal to M1 power k. So, I will write this as M1 power k up to Mn power k. This is contained in n power k, which is 0. This implies that M1 power k to Mn power k, this is equal to 0. Therefore, the 0 ideal is a finite product of maximal ideals of A, and A is Artinian. Therefore, that implies A is Noetherian. What about the converse? Is a Noetherian ring Artinian? Is a Noetherian ring, if A is Noetherian, can we say A is Artinian? Yeah? Kx or Z, any PID. If I look at an ideal, a non-zero element in any PID, then look at A, A to be non-zero element in PID, then we have this descending chain, A contained in A square, contained in A cube, contained in A power 4, and so on, that never terminates. It is a domain. So, it will never terminate, it will be strictly decreasing chain which will never terminate. So, therefore, an Artinian ring, Noetherian ring need not necessarily be an Artinian ring. But let us look at the let us look at this proof. What have we used to ultimately to conclude that A is Noetherian? To start with, we are starting with an Artinian ring. To conclude A is Noetherian, we showed that 0 is a product of maximal ideals. Now, suppose we start with A be a Noetherian ring. Okay? In a Noetherian ring, nil radical is nilpotent, right? Now, what condition can you think will ensure that 0 is a product of maximal ideals? Yeah, that is a see here, what are the conditions that we used in Artinian ring? These are the only prime ideals. If this were true in the case of the ring that we are starting with, then the whole thing goes through. We can just replace this by Artinian, here replace this by Noetherian, replace this by Artinian. Or in other words, if A is a Noetherian ring such that every prime ideal is maximal, then it is Artinian. That is what the proof says, right. If your ring, in your ring every prime ideal is maximal, then the nil radical is same as intersection, Jacobson's radical, which is same as nil radical is intersection of maximal ideals. Now, if your ring is Noetherian, nil radical will be nilpotent. That means the intersection of maximal ideal whole power k will be 0, which means this will again hold true. Once you reach this stage, the Noetherianness and Artinianness are equivalent. So, therefore, the converse of this is, if A is Noetherian and every prime ideal of is maximal, then A is Artinian. See, A is Noetherian the 0 ideal has a primary decomposition, right. the 0 ideal has a primary decomposition. Yeah. So let us write so 0 equal to Q1 intersection QR. Now each radical of Qi, so let radical of Qi be equal to Mi. Radical of Qi is equal to I mean this is a prime ideal, but our assumption is that every prime ideal is maximal. So radical of Qi is Mi. Now we proved another property of ideals in a Noetherian ring. Every ideal in a Noetherian ring contains a power of its radical, right. That means Mi power Ni belongs to Qi, is contained in Qi for some Ni. Okay. Now if I take n to be maximum of n1 up to nr, what can you say about m1 power, okay, I don't even require that. I can simply say m1 power n1 product mr power nr. This is contained in m1 power n1 intersection up to mr power nr. Now each one is contained in Qi. This is contained in Q1 intersection Qr, but this is 0. Now we are through. M1 up to Mr is product of maximal ideals is contained in 0, which means that they are equal. That means 0 is a product of finitely many maximal ideals, and that implies that A is Artinian because A is Noetherian. Okay. So this every prime ideal of A is maximal implies that it has only finitely many. So to say that, see, if you if a ring has only one prime ideal, need not necessarily imply that it is Noetherian or Artinian. Say for example, if I look at the ring R equal to K x1 x2, I mean infinitely many variables, okay, and look at the ideal I equal to x1 x2 square x3 cube and so on, okay, and take A to be equal to R mod I, then A has only one prime ideal, which is the ideal generated by, see, any prime ideal here will be a prime ideal containing this ideal. If a prime ideal contains I, it has to contain all the variables, but that is a maximal ideal. So the only prime ideal containing I is the maximal ideal generated by all the variables. So A has only one prime ideal. Right? Now this ring is neither Noetherian nor Artinian, right? If you look at the ideal generated by, so let M be the so x1 bar is 0, x2 bar, x3 bar and so on, the ideal generated by all the variables in A, then this is an infinite chain, x2 bar contained in x2 bar, x3 bar contained in x2 bar, x3 bar, x4 bar and so on. This is a chain here. Now can you think of a descending chain which never becomes 0? M square, M cube. When you do this, each time one variable drops, but it will never terminate, it will never become 0. If there were only finitely many variables, and if you look at something like this, m power n becomes 0, but here in this case none of them will become 0. So this ring is neither Noetherian nor Artinian. Now in a Noetherian ring, if your ring is Noetherian, something like that cannot happen, in the sense that suppose A is so let A be a Noetherian ring. I want a local condition here. Yeah, A be a Noetherian local ring. In fact, that is see, this is indeed a local ring, right? There is only one maximal ideal, there is only one prime ideal, which is the maximal ideal generated by the variables. Now let A be a Noetherian local ring with the maximal ideal M. Okay. So see, here the situation is that we have an increasing chain which never terminates and a decreasing chain which never terminates. In a Noetherian ring, there are only two possibilities. One is that m power n is not equal to m power n plus 1 for all n bigger than or equal to 1. Okay. And another option is m power n is 0 for some n. So let's assume, this is fairly straightforward conclusion. Suppose this is, see, it can be that there is a see, in this case what we say is that the ring is not Artinian, right. So a Noetherian ring can be simply a Noetherian ring which is not Artinian or an Artinian ring, but in the Artinian ring case this is always true. So that is exactly what we are saying. So in the Noetherian, in this case, if suppose m power n is equal to m power n plus 1 for some n. Suppose this is, this does not hold. So let me then precisely one of the below conditions hold. Below statements hold in A. Okay. Either this or this, both cannot happen together. If this holds true, well and good. If this is not true, that is, there exists some m power n which is equal to m power n plus 1. We are not saying that it is Artinian. Okay. We are simply saying that for this maximal ideal, m power n is equal to m power n plus 1 for some n. But then we are in a Noetherian ring case. M power n is a finitely generated module. I can write this as m times m power n up by Nakayama lemma by Nakayama lemma m power n is 0. So, once this is true, that says that your ring is Artinian. So, in a Noetherian ring, either it is not Noetherian or not Artinian. In that case, we will have this true, or in other case it will be Artinian, and in that case this is true. That is precisely what we have proved. Now, Artinian rings are more special than Noetherian rings. Now, we have already proved that in the sense that Artinian rings are Noetherian rings with some additional assumptions. Okay. But it is there are it is more generally and there are more stronger results which describe Artinian rings, which one can in fact give a very nice structure theorem. Every Artinian ring is isomorphic to a finite product of we should say unique in fact I should say every Artinian ring is uniquely is a finite product of Artinian local ring. Finite product of Artinian local rings, finite product up to unique up to isomorphism. What does that mean? What we are saying is that if I take an Artinian ring A, then I can write this A as A1 cross up to AN, where each AI is an Artinian local ring and each AI is uniquely determined up to isomorphism. That means if I have some A1 prime cross AM prime, this M is equal to N and AI is isomorphic to some AJs. So, how do you prove this? So, first let us let M1 let A be an Artinian ring. So, we know that there are all the prime ideals in A are maximal and there are only finitely many maximal ideals. So, let us write M1 up to Mn be maximal ideals of A. Okay. Now, this implies intersection of the product mi power k. This is, or the intersection 1 to n. This is equal to the product mi power k I from 1 to n. This is 0. See, this is nil radical. So, therefore, this nil radical is nilpotent. We just use the fact that nil radical is nilpotent to say that this will be 0. Okay. Now, let us recall a theorem that we proved some time back. If I have look at this I1 up to In, okay, they are all co-prime. This is co-prime if and only if the product is I is intersection Ij, and in that case what we know is that A mod A is isomorphic to A mod I1 power k cross up to I1 cross up to A mod Ik In. Right, when they are co-prime the intersection hold. So, if you send an email, if you send a map from A to this product, this will A going to x, A plus I1 comma up to A plus In, the kernel will be the intersection. So, this will be isomorphic to the intersection, which is also same as the product. What? This we have already proved. This is isomorphic. Now, let us bring it in our situation. What do we get? I look at A mod M1 power k cross up to A mod Mn power k. This is isomorphic to A mod intersection of M1 power k or the product, which is 0. So, A is, what we have shown is that A is a product of, now what can you say about this ring? Each if AI is equal to A mod Mi power k, then this is Artinian ring because A is Artinian, and this is a local ring. See, this Mi power k is a primary ideal which is primary to the maximal ideal. The only prime ideal containing this would be Mi itself. There are no other prime ideal containing. So, therefore, this is a local ring. Then AI is an Artinian local ring. So, what we have shown is that an Artinian local ring is an Artinian ring is product of Artinian local rings. Now we show that this product is unique up to isomorphism, in the sense that you start with, this is one isomorphism that we have exhibited. Now suppose A is isomorphic to product of some Artinian local rings, then those components cannot be different from these guys. That is what we would like to show. That will imply that it is the structure theorem, that would imply that it is unique up to isomorphism. Okay. That we will do in the next class.